lines, damn lines, and statistics. Most lines today are drawn with the linear function and a computer. They're feeding CNC machines or plotters or what have you. So it's necessary to give a little group of the formulas that work with that, with the computer, with the numerical application of the linear function. Also, statistics in its most basic form is the use of a line, the regression line, or the this, that, or the other line. And so it's a good idea to get a quick and easy way to look at that as well.
The linear function. The linear function. If you only want one piece of mathematics, this is it. You hear a lot of words in the tech world that all involve the linear function. Proportional, inverse proportional, linear, similar, small region, piston band, rectilinear, factor, coefficient, approximate, regression, slope, rate of change, primitive, naive, first attempt, constant, uniform, non-square, low order, scale factor, potential energy, laminar flow, resistive, and whatnot, especially the whatnot. I remember being in a meeting with a bunch of board engineers. When it was mentioned that something was a linear function, smiles erupted and all took out calculators. Start with the simplest function. Y equals x. X is the independent variable or input, and y is the dependent variable or output. The form f at x equals x is also used where f at x is the output. F at x stands for the function with x as the input. The graph of y equals x is a line going from negative y and x to positive y and x at a 45-degree angle. The line y equals negative x goes from positive y to negative y at 45 degrees. The two lines are at right angles. A more useful function is y equals mx, where x is the input or independent variable, y is the output or dependent variable, and m is the slope. Again, f at x equals mx is often also used. In this simple form, y, or f at x, equals 0 when x equals 0, so the line passes through the point 0, 0. Here, m, the slope of the line, equals y divided by x. Like I said, if you only want one piece of mathematics, y equals mx is it. Lots of people with advanced degrees leave the room at this point. Many have been too mathed to go on. What they need is a tiny set of math tools for doing everything in an understandable way. They need something they can feel comfortable using. Y equals mx is about as simple as it gets. Just a little more work and they will have a whole package of useful stuff, maybe more than they'll ever need. Now that we got that out of the way, here's the basic plan for the rest of this video. The general or universal linear function. Getting that function given 2 points. Approximating a difficult function. Getting the intersection point given 2 lines. Getting the line at right angles. Getting the midpoint of a line. getting the circle center given 3 points, getting the average of a data set, getting the trend of a data set, getting the error of the trend, and a gratuitous load of non-ex cathedra pontification. The universal function for the line is y, or fx, equals mx plus b, where y equals b when x equals 0. The line passes through the point 0, b. Drawing a line between 2 points with a ruler and chalk line is a basic skill. The same skill in the numerical world is getting the linear function given 2 points, x sub 1, y sub 1, and x sub 2, y sub 2. This involves finding the m and b for the formula y equals mx plus b. There are several ways to do this. Here is a simple one. Here are the 2 functions with m and b unknown. Y sub 1 equals mx sub 1 plus b, and y sub 2 equals mx sub 2 plus b. Subtracting one function from the other gives y sub 1 minus y sub 2 equals mx sub 1 minus mx sub 2 plus b minus b. The b's cancel. So y sub 1 minus y sub 2 equals m x sub 1 x sub 2. And therefore the quantity y sub 1 minus y sub 2 divided by the quantity x sub 1 minus x sub 2 equals m. We can get b from one of the points in m. mx plus b equals y, so b equals y minus mx. It is often useful to approximate a difficult function with straight lines. The lines are easy to understand. Even a small number of lines can do a good enough job for many applications. 2 points from the complex function are used to get the formula for each line. Here, 3 lines approximate the sine function from 0 to 90 degrees. The values of the sine at 0, 45 degrees, 60 degrees, and 90 degrees give enough points for 3 lines. The maximum error is around 3%. Here, 5 lines are used. The maximum error is less than 1%. In the real world, whatever that is, most things either are linear, can be made to be linear, or can be approximated well enough with the linear function. Sometimes an average needs to be thrown in for good measure. Getting the intersection point of 2 lines is the next most useful thing. Solving the 2 linear equations together gives the intersection point. Here are the 2 equations with x and y unknown. Subtract one from the other. Solve for x. So x equals minus the difference in the b's divided by the difference in the m's. Substitute x back into one of the equations to get y. As noted before, the lines y equals x and y equals minus x are at right angles. In general, the slope of the line at right angles to y equals mx plus b is minus 1 divided by m. we often need the midpoint of a line between 2 points. That can be gotten by averaging the x values to get the new x and the y values to get the new y. Here is the table of our results. There is a circle that can be drawn through any 3 points not on a straight line. To get the center point by drawing, find the midpoint of each chord, draw the right angle line from each midpoint to the intersection at the circle center. Here's how to get the center point numerically. Find the formulas for the 2 chords, get their midpoints by averaging, get the right angle line passing through the midpoints, and solve for their intersection. This uses all the tools on the above table of results. The first step is to get the formulas for the 2 chords. Averaging the x and y values give the midpoints to lines. The 2 right-angled lines passing through the midpoints intersect at the center of the circle. I promised statistics, so here we are. If you only want to know 2 pieces of useful mathematics, the best 2 would be the linear function and the average or mean. If you want to represent 10 numbers by one number, add them together and divide by 10. To get an idea of the truth of the average, subtract the average from each value to get each deviation, square the result to make it positive, average the squares, and take the square root of the average. This is called the RMS error, where RMS stands for root of the mean of the square. The root of the mean of the squared deviations. Since this is the standard way to get the deviation from the average, statisticians call it the standard deviation. Given a bunch of data, say global temperatures, it's useful to know the trend. Is the temperature going up, going down, or staying the same? There are 3 trends that can usually be of some interest: a straight line or linear trend, a steeper exponential or square law trend, and a cyclical trend. Here we look only at the linear trend. Though few statisticians are eager to agree, it is possible to get a good trend with just easy to understand averages. An interesting proof that indicates this by the way, is on page 365 and 366 of the classic text, What is Mathematics by Courant and Robbins. To get a linear trend with just the average, divide the data into two groups, usually a left and a right. Average the x's of each group and the y's of each group to get a point in the middle of each group. Average the x's. The average x's and y's can give us the trend line, but the trend can also be seen just by inspecting the two y's. If the right y value is higher, the trend is up. If the right y value is lower, the trend is down. More in-depth analysis requires solving for the y equals mx plus b of the trend line. First getting the m, then substituting to get b. To see the goodness of the trend, get the RMS error between the line and the data points. Get the squared difference of each data point from the line at that point, average the squares, and take the square root to get the RMS error of the line. Now two more trends can be gotten using the RMS error value. One line goes from the first line point plus the RMS error to the last point minus the RMS error. The other line goes from the first line point minus the RMS error to the last point plus the RMS error. This covers a good range of likely trend lines. Here is a data set with a good trend. Even with the error, all possible trend lines go up. Here's a data set with a bad trend. One of the trend lines points down while the other two point up. The spread of the data is too wide to give a reliable result. Finding the trend with averages is easy to understand. No black boxes and no use of the mathematician's favorite phrase, it can be shown that. In the old days, the course to take and hate was the calculus. Now it's usually statistics. It's the course that drives students to the math-free majors, the majors of the waiters and janitors working to pay off college loans. If it were known that the average could be the one formula that underpins almost all of data analysis, it might not be so scary. Most data analysis can be done with just 4 different averages. The average itself, the average error, usually called the standard deviation, or I call it the RMS error, the average error with sample size, called the confidence interval, and the average relation or correlation coefficient, which is +1 if 2 data sets perfectly zig together, and -1 if one zigs while the other zags. Although a statistics course will include a lot of wiseacring about hypothesis tests, the Fisher transform, philosophy, p-values, ANOVA, chi-squared, r-squared, distributions, probability, and the brilliance of the instructor's children, the 4 things in the above list can do most of the actual work. It can certainly be argued that work done with the simplest, most common sense formulas will be most trusted. The whole world can learn the formula for an average. Maybe that's all the world needs to achieve sanity.
I hope this video has been helpful, and thanks for watching.